on MS Teams. So if you have any question, you can send me a chat message there on MS Teams. I'll reply. And this is what I have just told, that class test 2 is scheduled from 10 a.m. On February 22, and the syllabus is dynamic programming, greedy algorithms, dynamic programming, divide and conquer, and then trees. Trees we will start today, and this binary search tree and ABL tree, this we will finish today and tomorrow. Okay. So what is tree data structure? What is the motivation and need for the tree data structures? We learned some elementary data structures in our programming and data structure subject. And most of those data structures are like linear data structures. So we studied arrays, linked list, stack, queue. Before that, what is data structure? Data structure is like a structure to storing data, and certain operations are allowed. So let me ask this question: what is data structure? So what is data structure? What is a data structure? Think of what are the fundamental data types in C or any programming language. It's like, for example, int or char or float. So if you investigate or carefully look at each fundamental data type, then you see that each data is capable of holding certain information, and only certain kind of operations are performed, are allowed. For example, int data type is allowed or is designed to store integers, positive and negative integers, and there you can do multiplication, division, and division is also within that int domain. For example, within the int, if you divide an int data type whose value is 3, and if you divide by 2, the answer will be 1. So abstractly, it is data structure, or it is also called an abstract data type. Abstract data type. This it consists of two things. One is data. Another is set of operations allowed. For example, if you carefully look at, say, int data type, it stores integers, and you can do arithmetic operations on that data. For more advanced data type like arrays or linked list, it can store a set of data type, a set of integers or a set of elements of same type. It is like a set. And what are the operations that are allowed? You can search whether an element there in the set or not, whether you can insert some element in the set, you can delete an element from the set, and so on and so forth. So these are like array, linked list, stack. What is a stack? It is again a sequence of. It is now. It is not just a set. It is a sequence of elements, and whose one end is sort of blocked, and on the other end is only open, and you can insert and delete. But insert and delete is allowed. They are allowed only from the open end. That is what is called stack. Queue. What is queue? Queue is also a sequence of elements of same type, but it has the two ends are of two special types. If you insert, it will be in one end, which is called the rear end of the queue, and if you delete, it will be from the other end, which is called the front end of the queue. So, but if you see that all these data types, starting from the basic data types like char, int, and float, and to this more advanced like arrays, linked list, stack, queue, and we'll see some more data type today, tree, and so on. Data structures, and we basically it is like they're storing some data. For example, int and char and those things, they can just store one variable, one element. They just store one element abstractly, and depending on what kind of element we are storing, the set of operations allowed, and those are the various data types, int, float, and so on. Now, the higher level is arrays and linked list. They can store a list. They can store a set of objects. And when I say set, it always means that a set of elements of same type. That is what is array and linked list. Now, a slightly more higher is that stack and queue. And then again, we'll see another data type, a data structure called tree. Now, why tree is sort of in some sense fundamentally different from like arrays, linked list, stack queue is that they are all are like linear data type. For example, if from we move from a data type like int, float to a linear data structure like array and linked list and so on, we have made a jump. Like the basic data types store only one element. Now the higher level data structures like arrays, linked list, and stack queue, they store a set of elements with certain special structures. Now, slightly more higher or some different way is a tree data structure where the data is not linear but hierarchical in nature. They're not like set or anything. It's like there is some hierarchy in the data. And for those applications, we use this hierarchical data structure called tree. Now, why we need hierarchical data structure? Again, because there is some need in many real world applications. The data itself exhibits some hierarchy. For example, if I want to store the directory structure of any operating system or any folder, now a folder can contain another folder, and that folder can contain another many folders and few files and so on and so forth. So you see that the data itself is hierarchical in nature. Devadita, please take the attendance. So,
Yes, Nishit.
yeah, if the data itself exhibits some kind of hierarchy, it is natural to use a data structure which can capture this hierarchy in the data, and that's why we need this sort of hierarchical data structure like tree and so on. Now, what are the typical operations? So, typical operations of tree on tree. Operations on tree. So, typical operations like first is of course insert, then delete, insert an element in the tree, then delete an element, then search for an element. These are the basic operations. On top of that, you can of course think of other operations like finding a max, a mean, and so on and so forth. Now, let's compare how or what are the efficiencies of these operations for these early data structures like arrays and linked list. So, see what was the running times of these operations in case of array and linked list. Now, how do arrays? Now, for array, there are two possibilities. One is that you keep the array sorted. That is one possibility, a sorted array. That is unsorted. We call array is meant to represent a set of elements. Now, for sorted array, insert. Can someone tell me what will be the complexity of insert if there are only
One.
n elements? Yes.
O1.
Sorry, O1. For sorted array, what will be the insert complexity? How will you insert an element in a
Log
sorted array in order one time?
login, sir. Not login, sir.
Log n. Can you please tell me how will you insert an element in a sorted array in order log n time?
We have to do the binary search to find the position at which we can
Correct.
insert the
But
element.
then how will you insert then?
Then we have to shift the
Yes. How
remaining
much
element.
time will that require shifting?
It will order in 90.
Yes. Yes.
The remaining
So no
order.
hurry. Just take your time and think. Sorted array, because of the shifting, you need order n time in worst case. Insert. Same for same reason, because of shifting, you need order n time for delete and searching whether an element there in the array or not. There you can do a binary search and you can take order log n time. On the other hand, if the array is unsorted, how much time you will need for insert?
Order one.
Order. How much time for delete?
Then order.
Order. You are shifting. And how much time for search?
Order.
Order. Because you have to do linear search. You see again, see that it's not like one data structure sorted array is better than unsorted array. It depends on application. It depends on how frequent your insert is versus your search. If your application is more insert oriented, delete takes both the delete takes same time. But if your application is more of an insert oriented, then unsorted array is better. But if your application is such that you are storing a dictionary, which is built once and it is sort of static, data is not changing much, then and most of the times will be on search, then it may be better to use sorted array, which can perform the search very efficiently. Okay? So same you can do for linked list. So how much is insert?
Order one.
Order. Say insert front you can do. Delete.
It's also order one.
Order one. By the way, when I say delete, it sort of we assume that we have already found the element we want to delete. Typically, from user's perspective, deletion often needs to search first. So if user says that delete 10 from this set, we first, both in array and linked list, we first need to search where the 10 is. So be careful about this delete. Let me put a star here. It's like deletion without search. Typically, deletion involves first searching whether the element is there or not and where it is, and then delete. Okay, and search.
Sir, order and
Order. Order. Okay. Now, the beauty of tree, or not of any tree, what we will see is we called a say a special kind of binary search tree. Binary search tree. It can perform all the operations in order log n time. Does that mean that there will be no applications or no cases where using an array is better than special binary search tree? There, I leave that question to you. Think about it. Answer. You should be able to answer before the end of tomorrow's class. Okay.
So can you repeat the question?
This look at this table. It shows that the special binary search tree, whatever this tree is, this can perform insert, delete, and search operations as good as in like linked list and sorted tree array or unsorted array. So from this, can I conclude that there cannot be any application where it may be better to use say sorted array in comparison with special binary search tree. At least this table gives that impression. Binary search, special binary search tree, whatever that means, what speciality we'll see, but it shows that this all the operations it performs as good as the other data structures listed in this table. Is the question clear?
So if the insertions and deletions take place only at one end of the list, then it is always better to not use a binary search tree.
And use linked list instead.
Yes, yes.
Good. Okay. Think about the other one also. For example, can you think of a sorted array? Can you think of an application where using sorted array is better than using special binary search tree? At least this table tells me that there can't be any application because for all operations, special binary search tree performs as good as possible, if not better than sorted array. So the answer is not in the table, and the answer you should be able to give at the end of our study of trees. Yes.
So maybe in the cases where we have a very large data set, since in the BST we need a set of pointers which point from one leaf to another, one node to another, whereas a sorted array does not need it. So the space required by a search tree
Correct.
is greater than that of an sorted array.
Very good, very good. You know, the devil is hidden in BO notation. Even in linked list, you see that, you know, to achieve big O of one time insertion and deletion in big O of one time, you know, with every data, you are storing a pointer. So in some sense, to store n data, you are storing n pointers. In array, are you storing any pointers? No. So although in asymptotically, you know, the storage is same in to store n elements, all these data structures like arrays, linked list, and special binary search tree stores big of n information, but the extra thing that is stored for array, it is 0. No, nothing extra is stored. It's like O of 1, maybe the starting address of the array. That's it. What is needed for array. But for linked list, we already see that the extra thing needed is other than the data is already ordered in other things that you are storing, which are pointers. For n plus 1. For special binary search tree, you will see that, you know, not only n, we will be storing like 2n or 3n, something like that. Okay. Yes, good. Okay. So in this lecture, we'll by tree we mean what is called rooted tree. It is a rooted tree. It is a tree where there is a special node called root node. And what is a rooted tree? What is the definition of rooted tree? Let me define. There is a root node, a root, and rooted tree is defined recursively, and it has few children, and this root is connected to its children by one edge, and each children is itself a root of a tree. You see the definition itself is recursive. So first of all, and for the base case, because the definition is recursive, define the base case properly. So empty set is an empty tree. This is just to handle base case of our recursive definition, an empty tree. Then you can define a rooted tree, and for some strange reason, I don't know why, computer scientists think that trees grow from top to bottom with root at the top. I don't know why, but that's the convention that the entire computer science community follows, and just for consistency, we'll also follow that. The root is on the top, and trees grow from top to bottom. So root node connected to its children each of which is a root of another tree. From this definition, we can make very easy but important observations. First observation: tree is connected. Every tree is connected. It is possible to reach from any node to any node. It is possible from the definition. It is clear that, again by induction, that it is possible to reach root node from any node, and between any node x and y, if it is possible to reach the root node from both x and y, then it is also possible to reach from x to y via root node. First take the path from x to root node, and then root node to y. Second is the observation is that number of edges is n minus 1, where n is the number of nodes. Can someone say why? Why it's an easy observation?
So n is the number of roots in the whole tree.
Yes, n is the number of nodes in the whole tree. Let me give a concrete example. Maybe say 7 is the root node, 5, 10, is a concrete example. So the number of nodes is 4 and the number of edges is 3. I say that this is not a coincidence. The number of edges will be always 1 less than the number of nodes. And it's just an easy observation from the definition, whatever I have said till now on trees. Can someone?
What
Yes.
do you mean by edges?
So these are the edges from root to leaf, root to children. These are the edges. For example,
Okay.
so this is one edge, here's one edge. Here, this is one edge, here's one edge, here's one edge, and so on. So, for example, in this concrete example, the number of nodes is 3, number of nodes is 4, and the number of edges is 3. Anyone?
Because it is connected.
Yes, connected, but so what? You know, every node is connected to its parent by one edge, and all the nodes has exactly one parent, except the root node. Root node does not have have any parent, and every other node has a parent, and that node is connected to its parent by only one edge. So the number of edges is n minus 1. Since every node except root node is connected to its parent by one edge. And these are all the edges. If you see all the edges, every edge connects a node to its parent. So if you view each edge like this, and the root node does not have any parent, so the number of edges is n minus 1. Is this clear to everyone? Why the number of edges is n minus 1? There are n nodes. Each node is connected to its parent by an edge, and these are the only edges. There are no other edge. And root node does not have a parent. So the number of edges is n minus 1. Okay, so here are a few terminologies. Let me just discuss with you. So root we have I have defined. Then of course parent. Parent is, for example, 7 is the parent of 5, 10 is parent of 8, and so on and so forth. Then children or child. For example, 5 is a child of 7, 10 is a child of 8, and so on and so forth. Okay. Then next, these are concepts. This is like hierarchy. Siblings. Like sibling is if two nodes are sibling if their parent is same. For example, 5 and 10 are siblings. Okay. Similarly, with the same idea, we can define grandparent. For example, 7 is a grandparent of 8. Grandparent is parent's parent. 10 does not have any grandparent. Similarly, children concept you can extend to grandchildren, grandchild. 8 is grandchild of 7, and so on. Okay, is this terminology is clear? I'm not formally defining it. It is not necessary. It is as clear as daylight. Is there anyone who want me to explain these terminologies again? Parent, child, because this entire structure is hierarchical. There is a root node, and it has some number of children. Each is a root of another subtree, and so on. So this is hierarchical defined. These are binary trees. Mm. Now you see, okay, conceptually I understand, but how will I code it? You know, in this entire subject, algorithms 1, we will talk about data structures, we will talk about pseudocodes, but we will reach or we will live at that point where it is crystal clear how to code. At this point, if I leave the definition of tree at this point, it is not clear how will I code it. So let me explain how will you code it. What you do, maybe for C, you define each of these node as a structure. Struct, let's call node. These are implementation of the tree. And there is some data. For example, in the root node, the data is 7. Each node has a data. Assume that the data is int. Does not matter if the data is float, you can, instead of writing int data, you can write float data. Whatever the data is, there are more data, you can write some more data. That is fine. That is not the problem. But the problem is that the number of children. How will I store the children? Children will be a pointer to another node. That is sort of clear. Is it, for example, 5 is the children of 7? What is 5? 5 is also a structure of like node. But how many children? A node can have, is allowed to have any number of children. How many fields I will reserve? There is no upper bound on the number of children that a node is allowed to have. It is not like China. Any node can have at most 2 children. No, it's not like that. So any suggestion? How can I? Maybe let me write an example. No, maybe I don't know. Write this way: A, B, C, D. It has many children. E. And B may not have so many children. C may have 2 more children, maybe F, G. D may have, I don't know, many children. It can have many more children. Doesn't matter. There is no upper bound on the number of children that a node is allowed to have. Then how will I store? Any suggestion? Is the problem clear? Anyone who wants me to repeat the problem, the question? We are talking about implementation detail. How will I implement this tree idea, tree data structure in a programming language, say C, C++, Java, doesn't matter. And what I'm proposing is that you to store them as structure. It makes sense. A structure is meant to be something which consists of logically connected but different data types. For example, if you look at a node, it has pointer to ages, pointer to children, which are also nodes, and it also has a data type, data like 7 and so on. So the data, I can write data, but how many children or how will I proceed? Suggestion, any suggestion? Is the question clear to everyone? And the idea is this. This is called, this is a serious concern, and the answer is what is known as left child right sibling representation. Right this way. What you do is that you only store a pointer to left child and another pointer to its right sibling. So left child. And another pointer to right sibling. Right sibling of whom? Of the left child, leftmost child. That's it. And this particular way of representing or implementing a tree is called, or representing a tree is called left child right sibling representation. Left child right sibling representation. So let's see, let's apply this representation on this concrete example. Let's take this tree. And using left child right sibling representation, Let's see how we'll do. A, this particular node, root node, will store this data A. It will, sorry, here I said that the right sibling of the left child, it's not the right sibling of the left child, it is the right sibling of itself. So let me expand this. So what is this root node is storing? It has three fields: data field A, the left child field. In the left child field, it will store the address of B, another node whose data field is B, and it will store a pointer to this node. And the last one, it will store right sibling. Does A have any right sibling? Does A have any right sibling? My screen is visible, right? I'm audible, right? This A, node A, does it have a right sibling?
No, sir.
No. Clearly, so it is null. Okay. B, does it have a left child? No. Null. Does it have a right sibling? Yes, C. So the right sibling will point to its right sibling. Right sibling means immediately right, a sibling which is immediately right of it. Okay. So C has two child. The left child is F. And this pointer points to F. And the right sibling is D. Is the representation clear to everyone? Similarly, D has many children, and if it will be null, and it will be G here again. Sorry. The right sibling of F is G. F does not have any children, so it will be null. And G does not have any children, null. And G does not have any right sibling, also null. And so on. Is the representation clear to everyone? This is what is called left child right sibling representation. Now, we'll study a special kind of binary tree, a special kind of tree which is called binary tree, and it's called a binary search tree. So two new adjectives are getting attached to tree. One is binary, another is search. What is a binary search tree? The word binary means that every node can have at most two children. Okay, every node can have at most two children. It is not allowed to have more than two children. A tree where a node is not allowed to have more than two children is called a binary tree. So for binary tree, representation is very easy. You know that the number of children could be at most two. So you define two pointers, struct node, maybe int data, then struct node, left child and struct node right child. Okay, so there is no need for going to the more complicated left child right sibling representation. There also we were storing 2 extra pointers per node. Here also we are storing 2 pointers per node. So there is we are not storing anything more or something like that. But what is that search thing? Search thing is that data is stored in the tree. So here, for example, these are the data 7, 5, 10, 8, and so on. Data is stored according to some rule so that the search operation can be made efficiently. Okay, so that is that rule to make the search operation in order log n time hopefully is what makes a tree a binary search tree. What is that rule? The rule is very simple. At every node, say x, take any node x, the values value, let me write data. The data stored in the left subtree of x is less than x, less than the data at x, and the data stored in the right subtree is more than the data stored at x. Okay, so for the time being, I assume that there is no duplicate. All data are distinct, and we have seen from our experience that these duplicates we just need some care. It does not need any difficulty or any sophistication in algorithm. It just need careful implementation, and this case is also same. So you just assume that there is no duplicate. Let's take some example. So maybe I don't know, maybe 100, 50, 30, 80. So for example, here if you see that in every node, the any data in its left subtree is less than the value at the node, the data at the node, and on the right subtree it is more than the value at the node. Okay, is this sort of clear? The definition of binary search tree. For example, if I add here maybe 250, is this still a binary search tree? Can someone unmute and tell me?
No, sir.
No. Why it is not a binary search tree?
So because the left subtree of 200 has a value 250.
The binary search tree condition is violated at this node because the left subtree has a value as less than 250. The left subtree has a value 250, which is more than 200, which is not allowed. This shows. So if I want to insert 250, where should I insert? Suppose I want to insert 250. Where should I insert? Can someone tell me? Can someone
left side of 300.
Left child of 300. And yes, you have learned how the insertion operation is done in binary search tree. You have learned how insertion and search is done. For example, if I want to uh, ask you, um, can you search for a node, say 350 is 350 or they are not? And suppose you are at the root, like linked list. For linked list, you store the head of the linked list. For array, you store the starting address of the array. For storing a binary search tree, you store the address of the root node, because from there you can reach everywhere. So how will you search if there exists a node whose data is 350? You are at the root node and you see that the data at the root node is 100. Will you go left or right?
So right.
Right. How can you go right? Because in the root node, other than data also, it is a pointer to left child, the left node, left child, which is 50, and a pointer to right child, which is 200. Now, because you are searching for 350, and the current at the current node the data is 100. If 350 is at all present, it can only be present on the right subtree. It cannot be present on the left subtree, because due to binary search tree property, all the data in the left subtree is less than 100. So I go to right subtree, right child, and I come at 200. Again, applying the same reason, I am looking for 350. If it is present, it can only be present on the right of 200. It cannot be on the left of 200. So I go to 300. Again, apply, and I see that again, if 350 is present, it can be only to the right of 300. It cannot be in the left of 300. And hence, I see that there is nothing in the right of 300. The right child, there is no right child. The right child pointer is null at 300. So I conclude that 350 is not present in the binary search tree. And this is the first step of insertion. If you want to insert an item, say 350, you first search. If you reach a node where 350 is there, then it is already there. And we are assuming that duplicates are not allowed, so we will not allow 350. We will do nothing. Otherwise, we will reach a node where the right child, it should be on the right or left in a place where our search key should be there, but there is empty. In that empty space, we create a new node with our search key and insert. In this case, I create a new node 3 with data 350, left and right child null, and place it as a right child of 300. This is the insert subroutine. Let's do another insert. Let's try to insert 90. Let's see how will I insert 90. Let me use some other color. I again start at 100. I'm searching for 90. 90, if it is present, it can only be in the left subtree of 100. I go to 50. If 90 is present, then it can only be in the right subtree of 50. I go to 80. And if 90 is present, it can only be in the right subtree of 80. And I see that in the right subtree, there is nothing. The right child of 80 is null. And so I create a new node with value 90. Left child and right child pointers are null. And I make it a right child of 80. Is the insertion clear? Let me ask somebody. Orgodip Pal?
Yes,
Yes.
yes, sir.
Please help me insert 40.
Can you repeat, sir?
Please help me insert 40. Dictate me how will I insert 40. I am at 100.
Oh.
How will I insert 40? 4040.
The first we will go to 50, and then we will go to the left subchild, which is 30. Then we will make a right subchild and insert 40, as 40 is bigger than 30.
Very good. Excellent. So my job is done today. So that's it for binary search tree. tomorrow I am out of time. Tomorrow we will continue our study of binary search tree. We will study deletion, and we will study traversals. What is traversal? You know, sometimes we want to list down all the elements stored. For arrays, we can start from starting address and traverse the array. They are consecutively stored. For linked list, I'm start at the head of the linked list and traverse the linked list. It's a linear list. But here it is not a linear list. It is a sort of hierarchical, spread across. So how will I list down all elements in the tree? And there are various methods of doing that. So tomorrow we'll study those traversals methods, traversing all the nodes in the tree, listing down the values, traversals, and then we'll study deletions, and then we will move to the special data structures, special trees. Because here, if you see, what is the running time of the of this insertion? In the worst case, it can take the order of longest route to leaf path. Is the length of our longest route to leaf path. Okay, so again, so this is just for motivating and this sort of thing. So we will again tomorrow I'll formally define what do I mean by path and what is leaf. Leaf is a node which does not have any children. In a binary tree, a node is called leaf node if it has zero children. So these things again we'll continue in tomorrow's class. Question. I'm out of time.
So
Feel free to leave if you have any other class, or if you want to leave, feel free to leave. Yeah. I'm here to answer questions. Okay, so there is no questions, so let me stop. You can, Devadruti, you can stop the recording, and we'll meet again tomorrow at 10 a.m. We will continue this our study of trees.